So, hello again, everyone. Hope you're keeping yourselves safe and washing your hands a lot. We've been talking so far about weak acids and bases, and we focused entirely on what are called monoprotic acids and bases. That means ones that are capable of donating or accepting one proton. We're now going to expand this to consider what are referred to as polyprotic acids and bases. As seen by the name, what it simply means is that a polyprotic acid is capable of donating two or more protons in succession, not all at one time, and a polyprotic base is capable of accepting two or more protons, again, in succession, not all at once. One of the classic examples of a polyprotic acid is phosphoric acid. Phosphoric acid is a triprotic acid. That means that it's capable of donating three protons in succession, and the formula, as we already know, for phosphoric acid is H3PO4. Now, because it has three protons that it can donate, there are three separate equilibria that exist in an aqueous solution. In the first step, H3PO4 acts as an acid, donates a proton to water, forms its conjugate base, a dihydrogen phosphate ion, and a hydronium ion. Ka for that, which is referred to as Ka1 for the first step, is 7.6 times 10 to the minus 3. The second step now is the dihydrogen phosphate, and also it is the conjugate base of phosphoric acid, but is itself still acidic because it can donate one of its protons. And it does that to another water molecule to form its conjugate base, hydrogen phosphate, and another hydronium ion. The Ka for that second step is about 6.2 times 10 to the minus 8. So it's much less than the first step. And finally, in the third step, the hydrogen phosphate, which is the conjugate base of dihydrogen phosphate, is still itself a weak acid. It can donate that last proton, which it does, to a water molecule to form a phosphate ion and another hydronium ion. Ka for that third step is about 2 times 10 to the minus 13. So you can see that in these three successive steps, each successive one is about 5 orders of magnitude less than the preceding one. 10 to the minus 8 versus 10 to the minus 3, and 10 to the minus 13 versus 10 to the minus 8. So, and as it says here, typically, this is approximately true for most polyprotic acids. The Ka2 is typically about 10 to the minus 5 times the Ka1, and the Ka3 is about 10 to the minus 5 times the Ka2. Now, all polyprotic acids are weak ones, except for one important exception, sulfuric acid. For sulfuric acid, the first proton, it's a diprotic acid, of course, the first proton, which is donated to a water molecule to form a hydrogen sulfate ion, conjugate base of sulfuric acid, and a hydronium ion, it behaves like a strong acid. The Ka is on the order of 100 or slightly higher. And so for that reason, in a solution of sulfuric acid, as we've come to expect, a solution of sulfuric acid contains the same number of hydronium ions as there were sulfuric acid molecules to begin with. In other words, a solution that's 0.1 molar H2SO4 is essentially 0.1 molar in H3O+. But the second step, the one that involves hydrogen sulfate ionizing, as shown here, to form sulfate ion, is a weak acid. It's still not among the weakest of acids, but still it's about 4 orders of magnitude lower than the Ka1. So it's about 1.2 times 10 to the minus 2. This is for sulfuric acid only. All other polyprotic acids are weak, even the first step. And so what's shown here, and your book has a similar table of several polyprotic acids, all of these are referred to as stepwise equilibrium constants because, as I said, a polyprotic acid doesn't donate all of its protons at once. Each one goes through a succession of steps where it forms its conjugate base, which can then act as another weak acid. So there are several inorganic acids here. Hydrogen sulfide, as we know, is a gas, but when it behaves as an acid, it's referred to as hydrosulfuric acid. In solution, hydrogen sulfide will first form HS-1, and then the second step forms sulfide, S-2. Its first step has a pK of about 7, and the second one is about almost 14. What that tells you is that the HS2 HS minus is a very weak acid, and conversely, the sulfide ion then, S minus 2, is a very strong base, which it is in fact. It's almost as strong as hydroxide ions. There are several other examples here. Here's the sulfuric acid we just talked about. Sulfurous acid also has 2 protons, but even the first one is a weak acid. pKa1 is almost 2, and pKa2 is about 7. Here's the sulfuric acid we just talked about. There are several others here. Phosphoric acid that we just discussed is here. The pKa1 is 2.1, and the pKa2 is 7.2, and the pKa3 is a little less than 13. Now, this is phosphorus acid. It's similar to phosphoric. It's H3PO3 instead of H3PO4. And at first glance, you would think, well, it's another triprotic acid like phosphoric acid, but it's not. Nature is not always predictable. And here is what you would get if you followed all the rules and drew a Lewis dot structure for phosphorus acid, H3PO3. In drawing it this way, you would be satisfying the rule that you minimize the formal charges. This structure, you can go through, I won't go through all the details of it, but all of the atoms in the structure have a formal charge of 0. The 3 hydrogens, of course, are sharing just 1 pair of electrons. The 3 oxygens are all sharing 2 pairs and have 2 lone pairs, and so on. So all of the atoms in phosphorus acid have a formal charge of 0. However, that's not the preferred structure for phosphorus acid. It actually exists, and this is not exactly a resonance structure. A resonance structure, remember, is one in which the skeleton remains the same, but double bonds are in different positions. Well, this has no double bonds, so there are no resonance structures of it. However, it equilibrates with this material in water. And in fact, the equilibrium, as shown by the length of the line here, is far toward the right. It's far toward this structure, which is this one. Now, in this structure, one of the 3 hydrogens is bound to phosphorus, not to the oxygens. The other 2 are bound to the oxygens, and the 3rd oxygen, in fact, has no hydrogens on it at all. And so as a result, this oxygen has a formal charge of -1, and the phosphorus is left with a formal charge of +1. So this is a violation of the rules we talked about last semester, in which formal charges are preferably minimized. In the case of phosphorus acid, they're not. And in fact, for this reason, phosphorus acid behaves like a diprotic acid, not a triprotic one. So if we go back to this table here, you can see that in the case of phosphoric acid, there are 3 pKa's given, but for phosphorus acid, there's only 2. And that's the reason, because it's a diprotic acid, not a triprotic. Anyway, there are several more examples here of other inorganic acids. There are several examples here of organic acids, and as it turns out, many of the polyprotic acids that you'll encounter as you go along are organic molecules, not inorganic ones like the one shown here. Now, here is a summary of some of those diprotic acids that are organic. The simplest one is called oxalic acid. It consists of, let me blow this up a bit so you can see it better. It consists of 2 carbons, here and here, that's these 2 right here, each of which has a double bonded oxygen and an OH. That's called a carboxylic acid. It's the dicarboxylic acid. And so the 2 protons that are donatable, of course, are this one and that one, 2 here. And it turns out that the pKa1 for oxalic acid is 1.3, and the pKa2 is 4.3. Now, you can see that although the Ka then for oxalic acid, the Ka1, is on the order of 7 times 10 to the minus 2, it's not a terribly weak acid, but it's definitely not a strong acid. And the pKa2 is on the order of something times 10 to the minus 5 for the Ka2. Now, look what happens when in between these 2 carboxylic carbons, we put a CH2 group. These hydrogens are not donatable. They're just part of a hydrocarbon. Now, when the 2 carboxylic acid groups are farther apart, it looks like this. There's this extra carbon right here. Now, the pKa is higher. That means that the Ka is more negative. It's a less strong acid, and the pKa2 is the same. So that by separating these two groups by one additional carbon in between, the acid is weaker, both the Ka1 and the Ka2. The same thing happens when we put two extra carbons in between. There's two CH2 groups here. Now the two carboxylic acid groups are farther apart yet. Now looks like this. And now the acid is still weaker. Now the pKa1 is 4.2 and the pKa2 is 5.4. Now remember what we talked about, what makes an acid, a weak acid, weaker or stronger. Anything that weakens these OH bonds will make the acid stronger. Anything that strengthens them will make it a weaker acid. So evidently, among these three that we just considered, the ones with the weakest OH bonds is the oxalic acid. The second weakest is malonic acid, or propane dioic, and third is the butane dioic acid. But now notice what happens when we insert still more CH2 groups. Here's 3 of them, 4 of them, 5, 6, 7, and so on. Now the two carboxylic acid groups are farther and farther apart. And notice what happens. Once there are as many as 2 carbons in between, addition of further carbons, making them a longer and longer chain and putting the two carboxylic acid groups farther and farther apart, has essentially no further effect than weakening the acid. The Ka1s for all of these are virtually the same, and so are the Ka2s. The pKa2s are shown here. Now, in fact, this last one has a total of 8 CH2 groups in between. There can be 9 and 10, and they have even longer names, undecane dioic and dodecane dioic acid. And in fact, they have about the same pKa 1s and 2s as well. Now, it turns out that these, the formation of these things, go back to this one right here so you can see them all at one time. All of these have what's called an IUPAC name. IUPAC, as I mentioned once before, stands for the International Union of Pure and Applied Chemistry. They're the overseers internationally of nomenclature in chemistry, assigning correct names and so on. And their names are derived from the simple fact that all of these are diprotic acids, so they're all dioic acids. Notice that they all end in dioic acid. And the first part of the name is a reflection of what hydrocarbon it's derived from: ethane, propane, butane, pentane, and so on. So this first one is called ethane dioic, propane dioic, butane dioic, and so on. However, essentially no practicing chemist refers to them by these names except for very formal purposes. They're all referred to by their common names, which have been known for many more years: oxalic, malonic, succinic, glutaric, adipic, which is used to make nylon, pamelic, suberic, azelaic, and sebacic acid. Now, as a mnemonic to aid remembering those names, and you may think it's kind of silly, but this is what we were taught when I took organic chemistry. If you look at the first letter of each of these names, O, M, S, G, A, P, S, A, and S, stands for "Oh my, such good apple pie, sweet as sugar." There you have it. You may learn that next year when you take organic, or you may not. I'm not sure what they do nowadays anymore. All right, so now we're going to consider another way of looking at these polyprotic acids. And in fact, they're referred to as alpha plots. And what they do, at first they may seem confusing, and I'll try to go through this and explain to you why we're doing this and what the relationships are between these various species. They're called alpha plots because they reflect the concentrations of an acid. This is now a monoprotic acid. Again, this is acetic acid. They refer to the concentrations of the monoprotic acid and its diprotic, its monoprotic conjugate base. So acetic acid, of course, its conjugate base is acetate ion. And what these plots all show is exactly this. It shows the concentrations of the various possible species. In the case of acetic acid, there's only 2, acetic acid itself and acetate. For polyprotic acids, there are more than 2 species, as we'll see in a few minutes. So the alpha essentially refers to the fraction of the original acid that has dissociated, that it's still present as the undissociated acid. And so as a function of pH down here, you'd say, well, if I make a solution that's, let's say, 1/10 molar in acetic acid, as we've seen for some example problems we talked about last time, the pH of that solution will be around 4-ish or something like that. So how do I get the pH to be only 2? Well, a simple way of doing it is to have a solution that's acetic acid and then add a strong acid to it, something like hydrochloric acid, an acid that doesn't interact with the acetic acid at all. And so if I add enough acetic acid to enough hydrochloric acid to the acetic acid solution, I can lower the pH to 2 or even lower. But let's say that I added enough to make the pH be 2. So now, as the pH increases, now how do I do that? Well, a way of doing it is to add a strong base, like sodium hydroxide. Again, something that is not involved in the acetic acid dissociation. So what I have at a pH of 2 is a solution that is all acetic acid. No acetate ions are present, as you can see. Concentration of acetate ions is essentially 0 down here. And all of the acetic acid is present as acetic acid. As I increase the pH by gradually adding a strong base like sodium hydroxide, what will happen is the pH will start increasing. As it does, what you will see is that the fraction of acetic acid that is dissociated gets less and less, gets more and more. More and more of the acetic acid is dissociated, and the acetate ion that comes from it, its concentration is going up. Its alpha portion of the 2 possible species. Eventually, when you get to a certain pH, right here, the concentration of acetic acid and acetate are exactly equal. That pH, it turns out, is the pKa of acetic acid, and I'll show you why in a minute. As I continue to add more and more base and make the pH go up, the fraction of acetic acid that's present keeps decreasing, and the corresponding fraction of acetate keeps increasing until eventually, at a pH of around 7 or higher, all of the original acetic acid is now dissociated and it's all present as acetate. So at this point right here, if I had been adding sodium hydroxide as a way of increasing the pH, what I would have is a solution of sodium acetate. There would be essentially no acetic acid remaining. So now let's look at the equilibria that are involved here, and so you can see where the statement I just made comes from. The pH at the point where the 2 curves cross, right here, is the pKa. Why can I say that? Well, at the point where the 2 curves cross, it means that the concentration of acetic acid is identical to the concentration of acetate. They both have the same concentration at that point, of course, because they're crossing here, they're equal. So if I look at the equilibria that are involved here, here's the dissociation equilibrium of acetic acid. We've seen this before. Acetic acid equilibrating with acetate to give hydronium ions, and the Ka expression, as we've seen before, is the concentration of acetate divided by the concentration of acetic acid, and then including the concentration of hydronium ions here in the numerator. Well, if the acetate concentration and the acetic acid concentration are equal, then this whole thing reduces to just concentration of hydronium ions. And so the Ka at that point, the pH at that point is minus the log of the hydronium ion concentration. And so what we can say is that at the point where the 2 curves cross, that pH, which on here looks like it's around 4.7 or so, that is the pKa of acetic acid. And there it is. That's why it turns out that way. So now, that's for a monoprotic acid. Let's look at the situation for a diprotic and triprotic, which is where these so-called alpha plots are more useful. For a diprotic acid, like let's say carbonic acid. Carbonic acid is produced when you dissolve CO2 gas in water. It's what makes sodas fizzy. So we'll just abbreviate it as H2A, where A is carbonate, and of course the 2 hydrogens are these 2 hydrogens here. So now there are 2 equilibria, unlike the monoprotic acetic acid. There is the carbonic acid plus water going to hydrogen carbonate, Ha minus, plus a hydronium ion. The Ka1 for that step, of course, is the the hydrogen carbonate concentration times hydronium over the carbonic acid concentration. The second step is hydrogen carbonate ionizing with water to produce a carbonate ion and another hydronium. The Ka2 for that step then, of course, is the concentration of A2 minus times the hydronium with the HA minus. So unlike the acetate, the acetic acid situation where only two species are possible, acetic acid and acetate ion, in the case of a diprotic acid, like carbonic acid, three species are possible: carbonic acid, hydrogen carbonate, and carbonate. Now, the concentrations of all three of those will vary with pH, just as we talked about for acetic acid. Now it gets a little bit more complicated. Don't worry about this. You don't have to remember that. This is just to make it complete, so that you can see what's going on. So let's go down here to the alpha plot for carbonic acid. Here's the carbonic acid, H2CO3, and again, this one covers a pH range all the way from 0 to 14, which is necessary because of the nature of carbonic acid. And so if I made a solution of pure carbonic acid in some way at a certain concentration, it would have a certain pH determined by its two Kas. But if I make the pH be 0, that means it's 1 molar in hydronium ion. I could do that by adding hydrochloric acid until the pH is 0. So at that point, the concentration of the carbonic acid, the H2CO3, would be 100%. The fraction of the species of carbonic acid is 1. It is essentially undissociated if the pH is that low. If I now start increasing the pH again by adding, let's say, sodium hydroxide solution, the pH will start going up. 1, 2, 3, 4. By the time you get to a pH of 4, now the pH is high enough that some of the H2CO3 starts disappearing and forming hydrogen carbonate right here. So as the H2CO3 decreases with increasing pH, the HCO3 minus increases with increasing pH until eventually, again, just as for the acetic acid, the two concentrations become equal right here. They cross at that point, so that the concentration at this point of H2CO3, HCO3 minus are equal. The pH at that point, which is 6.37, is a pKa1 of carbonic acid. Now, as I continue to increase the pH by adding more sodium hydroxide, the concentration of hydrogen carbonate will keep increasing until it reaches a maximum at around a little higher than a pH of 8, right here. As it turns out, at that point, the concentration remaining of H2CO3 is now very small. It's not quite 0 at that point, but it almost is 0. And the solution then consists of primarily hydrogen carbonate. I would essentially have a solution at that point of sodium hydrogen carbonate. Now, if I increase the pH still further by adding more sodium hydroxide, now the hydrogen carbonate starts disappearing because it is dissociating into carbonate. So the carbonate concentration starts going up. The hydrogen carbonate keeps going down until again, at a pH of 10.25, they become equal. The pH at that point, 10.25, is the pKa2 of carbonic acid. If I increase the pH still further by adding more sodium hydroxide, I eventually get to a point above about a pH of 13, where all of the carbon-containing species exist as carbonate. There's no hydrogen carbonate and no carbonic acid remaining. And so at that point, I would essentially have a solution of sodium carbonate, if sodium hydroxide is what I was adding to increase the pH. So that's the situation for all dicarboxylic acids. They behave, not carboxylic, excuse me, all diprotic acids, they all behave this way. They have three possible species present: the original acid, its conjugate base, and then its conjugate base. So these are the three species present, and the amounts of them that are there depend on the pH. The higher the pH, the higher are the concentrations of the increasingly dissociated species. So let's go back now and look at a triprotic acid to complete this gory picture. For a triprotic acid now, there are 3 equilibria, as we saw for phosphoric acid before. So that means that there are 4 species possible in solution. If our H3A is phosphoric acid again as an example. The four species that are possible are phosphoric acid. Its conjugate base is dihydrogen phosphate. The dihydrogen phosphate can dissociate to form hydrogen phosphate, its conjugate base, and that can dissociate further to form phosphate, which is the conjugate base of hydrogen phosphate. So there are four species possible: the H3A, the H2A minus, the HA2 plus, and the A3 minus. Each of them has its own equilibrium expression. I'm not going to go through all the details of this. You can look at these and see what it's exactly analogous to what we just talked about for carbonic acid. And so now if we look at the resulting alpha plots for the four species that are possible for phosphoric acid, it looks like this, as you would have expected from what we just saw for carbonic acid. At a low enough pH, again, that I could get by adding hydrochloric acid to the thing, excuse me, I would have a solution that's essentially all H3PO4. As the pH increases by adding sodium hydroxide, the H3PO4 decreases, the H2PO4 minus increases until they are equal at a pH of about 2.12, and that is the pKa1 of phosphoric acid, as we just saw before. Excuse me. With a further increase in pH, when I reach a pH of around 5 or thereabouts, essentially all of the phosphorus-containing species in solution is dihydrogen phosphate. A further increase in pH causes the dihydrogen phosphate to start ionizing some more, producing hydrogen phosphate. They cross and become equal at a pH of 7.21, which is the pKa2 of phosphoric acid. And with further increase, the dihydrogen phosphate keeps decreasing. The hydrogen phosphate becomes essentially the only phosphorus-containing species among the four at a pH of about 10. And then finally, with a further increase in pH to up to 14, virtually the entire solution is phosphate and some hydrogen phosphate remaining. Excuse me. Now, one of the things that you'll notice from this is that even at a pH of 14, the phosphate ion, there is still some phosphate and still some hydrogen phosphate remaining. The reason for that is because hydrogen phosphate is a very, very weak acid, which means that its conjugate base, phosphate, is a very strong base. In fact, the phosphate ion in solution is as strong a base as hydroxide ions are. And this is the reason why you don't have to have all of this forming with the sodium hydroxide you added, because it will behave as just as strong a base as sodium hydroxide does. But these are the alpha plots for both a diprotic acid, carbonic acid, and a triprotic acid. What these alpha plots illustrate is, and the point of them is to show how the concentrations of the various possible species are interrelated as a function of pH, as we'll see when we talk in the next section about buffers, is that this relationship between acids and their conjugate bases and vice versa are essentially what determines how buffers behave, as we will see. But you can see that the pH of the solution is what determines which species are present and in how high a concentration. Here's one other example. This is citric acid. You know what citric acid is, of course. It's present in citrus fruits. It's responsible for their sour taste. Citric acid is a 3-carbon acid. There's one carbon here, and one here, each of which has a carboxylic acid group attached to it. This one, and that one. This OH here is attached to the central carbon, but that hydrogen is not donatable. The OH group remains intact. Excuse me. As before, if I go through a sequence of increasing the pH, starting with a solution of citric acid, this stuff right here, with increasing pH, the citric acid concentration will start decreasing. The diprotic citrate builds up. Eventually it decreases. The monocitrate builds up, and then it decreases. And finally, at a high enough pH, all that's there is the citrate ion. Now, this is what not going to go through any of the numbers involved here, except that you can see that behavior looks much the same as it did for phosphoric acid. But this is a very important equilibrium system that has to be taken into account in the food industry, because citric acid is one of the components of soft drinks, especially ones like Coca-Cola and Pepsi-Cola and so on. So the concentrations of all of these species are determined by the pH, and the pH of the solution is adjusted very carefully when they manufacture these things to have the concentrations of these four species be exactly balanced in a way that provides something that is tasty but not corrosive. And so the typical pH of a soft drink is right around here, about 4 or thereabouts. And so you can see that at that point, the citric acid is decreased to only about 10% of the original amount. And most of what's there is the dihydrocitrate ion right here. And that's what is responsible for giving the level of sourness to soft drinks. So one final example here, ascorbic acid, which is vitamin C, which we all know about. Vitamin C is essentially ascorbic acid. It's a diprotic acid. Here's what's called the reduced form looks like. These hydrogens right here and here are the ones that are donatable. Now you'll notice that this does not look the same structure as the carboxylic acid, but they behave the same. These two protons are the ones that can be donated to form the so-called oxidized form. And it is this back and forth equilibrium that is responsible for the way vitamin C behaves in our bodies by donating and accepting protons. It's one of the things that actually adjusts the pH of our blood and other bodily fluids. So that's what we're going to be talking about for today. And excuse me, I forget. Minimize that, which he doesn't seem to want to do. And what I'm going to do is to continue this material next time when we talk about how these things are interrelated as a function of pH and a function of concentration. So